So you are at IIT Bombay, right?
Yes, yes.
All right, with the go signal from Amit, let us begin. I welcome you all to the first session of fourth day of this Group Theory Sangam conference. And our first speaker today is Sumit Chandra Mishra. He is a postdoctoral fellow at IIT Bombay and is going to speak on local global principles for norm 1 tori and multinorm tori over semi-global fields. Dr. Mishra, over to you.
Thank you. First of all, I would like to thank all the organizers for organizing this beautiful conference and for giving me a chance to present here. So I'm going to talk about local global principles for norm 1 tori and multinorm tori over semi-global fields. So I'll start with number fields first. So let F be a number field, and for example, just the field of rational numbers, and let omega F be the set of places of F. So we are taking Archimedean places and as well as non-Archimedean places. Then for every place nu, we use F sub nu to denote the completion of F with respect to nu. And let X be a variety over F. So then if we have a variety over F, then usually we are interested in knowing whether this X has a rational point over F or not. So I'm actually going to consider a related question. So the question is, if X has a rational point over all these completions F nu, then does that imply that the X has a rational point over F itself? So if the answer to this question is yes, then we say that the local global principle holds for X over F. And of course, then the next question is, why is this useful? So usually the thing is that these completions, this F nus, in this case are going to be the field of real numbers or field of complex numbers or periodic fields QP or their extensions. So and usually it's easier to decide if the variety X has a rational point over these fields. So let's see an example really quickly. So let F be the field of rational numbers, and so in this case the places will be just for every prime finite prime P we have a place, and then we have an non-Archimedean place which we denote by infinity. So the completions here are QP and the completion here is R. And let F be a quadratic form which is given like this. It's in n variables. And then we can consider the projective quadric which we will denote by X sub F associated to this. So then X sub F has a rational point over these fields Q or QP or R if and only if there exists a non-trivial zero of F over Q or QP or R. By non-trivial mean not all of the entries are zero, because that is obviously a solution. And also in this case we'll see that it is easier to decide whether F has a non-trivial zero over reals or QP. For example, we know that our reals F has a non-trivial zero if and only if all the coefficients are not of the same sign. And for periodics, we know that if the number of variables n is greater than or equal to 5, then there is always a non-trivial zero. So using this, we can so we see that we know a lot about quadratic forms over these completions. And finally, we have this theorem of Hasse, so which says that a quadratic form F over Q has a non-trivial zero over Q if and only if it has a non-trivial zero over R and QP for all primes P. So in other words, over Q, the local global principle holds for the quadrics X sub F associated to quadratic forms F. Okay, so However, in general, the local global principle does not always hold. It fails to hold for varieties over number fields in general. And there are deep results concerning when the principle holds, and in case it does not hold, then what are the possible obstructions to this principle, at least in the case when X is a torsor under a connected linear algebraic group. So with that, I would first talk a little bit about torsor. So what is a torsor? So let F be any field and G be a linear algebraic group over F. So just think of GLN and close subgroups of GLN. Then we can define torsor as follows. So this is we say that a F variety X is a G torsor over F if there is an action of G on X such that for every field extension L over F, if we look at the induced action of L points of G on L points of X, then it is simply transitive. So by this, I mean that if you pick any 2 points, say x1, x2 here in L points of X, then there is a unique element G here in L points of G, which takes x1 to x2. And so with this, now we can define what do we mean by local global principle for algebraic groups over numbered fields. So we say that the local global principle holds for an algebraic group G if for all G torsors X, if the torsor has a rational point over all the completions, then it has a rational point over F itself. So if this is true, then we say the local global principle holds, otherwise we say it fails. So in this talk, I am mostly considering a special kind of algebraic groups called norm tori and multinorm tori. So what is a norm torus? So let again F be any field and L over F be a finite separable extension, or you can think Galva if you like. So let GM be the multiplicative group, and then let R sub L over F GM denote the Weyl restriction of this multiplicative group. Then we define norm torus as follows. So from this Weyl restriction to GM, of GM to GM, we have a norm map. So this is just basically coming from the usual norm map from L star to F star. So we have this homomorphism of algebraic groups, and then we just take the kernel of this homomorphism. So we get an algebraic group. That algebraic group we denote by T sub L over F, and we call it norm torus associated to this extension L over F. So for this torus, the F points are actually just given by elements in L star whose norm is 1. So that's why we call it norm 1 torus, and we call it torus because it is actually a torus. By that I mean when you base change to separable closure, you just get copies of GM. Yeah, and actually obviously you don't need to go to separable closure, you can just go to L to check this, but it's fine. Okay, so this is what we call norm torus. Similarly, we can, instead of one extension, we can have multiple extensions. So let's say we have L1, L2, and so on, LM, all finite separable extensions. And we'll let L denote, L be the product of these extensions. So again, I'm actually using the same notation as before for the multinorm torus. So here again, for every Weyl restriction of GM to GM, we have a norm map. So then we consider just the product of these and the product of the maps. So again, we have a map for algebraic groups. We just take the kernel of that and we call it norm torus, multinorm torus associated to these extensions LIs. Okay, and actually the F points of this is also have a similar description. Okay, the L points of here, okay, I think there was some problem with the slides. Okay, so the L points of this also has the similar description, it is just the tuples in this allies, so that if you take the norm and take the product, that is 1. So that it has a similar description. So now we want to talk about local global principles over these algebraic groups. So I should first talk about what are the torsors for these algebraic groups. So again, we'll use the notation from before for the norm 1 tori and multinorm tori. So now let's let lambda be any f star element in f star. So we can define a variety which we denote by x sub lambda. So the way we define this variety is we just set the norm equals lambda. So norm gives us a polynomial, and then we just set it equals lambda to lambda. So that is a variety, and this has an obvious action of norm 1 torus on this. Norm 1 torus this T sub L over F, because any two elements whose norm differ by lambda, their difference is they differ by a unique norm 1 element. So that determines an action of norm 1 torus on this variety, and that makes this into a torsor under that group. So these varieties are torsors, and these are all torsors up to isomorphism. And here's a remark. So this x sub lambda is a trivial torsor under this group T sub L over F, if and only if lambda is in the norm map from L to F. So okay, I should say what do I mean by trivial torsor. For any group G, a G torsor is defined as follows. So G acts on itself by left multiplication. So that makes G into a G torsor. So any torsor which is isomorphic to this torsor, this particular torsor, is called a trivial G torsor. Similarly, for multinorm tori, if we have a bunch of finite separable extensions L1, L2, and so on Lm, then similarly the torsors will be given by just we set the product of norms equal to lambda. So this will be a torsor under this multinorm tori T sub L over F. Okay, so now we can talk about local global principles for these groups. So let F be a number field and L over F be a cyclic extension. Then this is a classical theorem of Hasse. So this is one of the first results of this kind. So it says that the local global principle holds for the norm 1 torus T sub L over F. So we have assumed that this is a cyclic extension. So of course he did not state it in this way, in this language. So this actually what this means is for any lambda in F star, if lambda is a norm when we base change to these completions, then and that is true for all the completions, then lambda is actually a norm from L star to F star. In other words, if lambda is a norm, lambda starting from F star, if it is a norm locally everywhere, then it is a norm globally. So of course the next question is what about extensions that are not necessarily cyclic? So then actually the local global principle for norm 1 tori fails even for abelian extensions, and one does not have to go very far. There is just by quadratic extension one can consider. So for example, you start with a field of rational numbers, and for the extension you just adjoin the square root of 13 and the square root of 17. So here 25 will be a norm locally everywhere, but it will not be a norm globally. So this is a counter example to the local global principle. And similarly, so what is known for multinorm tori? So here I'm actually considering a very specific case. So I'm just considering quadratic extensions. So let L1, L2, and so on, Lm be some quadratic extensions. And I should actually, for this problem, one should just consider non-isomorphic extensions, because if they are isomorphic, then you can just ignore, you can just consider one copy. So if M is 2, so if there are 2 extensions, quadratic extensions, then the local Google principle holds for multinomial to right. So this is due to Hurleyman in 1984. And then for M equals 3, actually there are counterexamples. It does not hold in general. But then the surprising thing is it holds. It again holds once you go after 3. So from 4 onwards, it holds. So this was proved by Eva Bayer, Flippinger, Tingyu Lee, and Raman Parimala in 2019. Okay, so and also there is this another in another direction. If we have 2 linearly disjoint Galois extensions, then Desmarches and we proved that the local Galois principle holds for the multinomial torus T sub L over F. Okay, so today we are actually going to consider some different class of fields called semi-global fields. So what is a semi-global field? It is a function field of a curve over a complete discretely valued field K. So let's just see some examples. So for example, we can actually start with any field, take Lorentz series over that. That is a completely discretely valued field, and then you can take function field of a curve or the function field of a P1 if you like. So you get this field. Similarly, you can maybe start with QP. QP is already a discretely, completely discretely valued field, and then take function field over that. Or you can take any field, finite field, or any field you like. So in these examples, I'm taking the curve to be P1, but you can take some more weird curves. So you get something like this. So these are our, some of the examples of semi-global fields. So now I'm going to define what do I mean by local Google principle for algebraic groups over these kind of fields. So again, so here let F be a semi-global field, and let G be a linear algebraic group over F. So I have to for number fields we took all the places. So here I'm going to take all the discrete valuations on F. This omega F. Then for every discrete valuation, we again use F nu to denote the completion of F with respect to that discrete valuation nu. Now again, just as in the case of number fields, we can define local Google principle for algebraic groups as follows. We say that the local Google principle holds for G, for all G tosses X, X has the rational point over all the completions, implies it has a rational point over F. Okay, so now we consider the case of norm to right for cyclic extensions over semi-global fields. So it follows from work of Polyethylene, Parimala, and Suresh that the local global principle holds for cyclic extensions in this case. This was true for number fields as well. Then we can ask, it's natural to ask following questions. So if F is a semi-global field and L over F be a Galois extension, then does the local global principle hold when this extension is not necessarily cyclic? Or more generally, we can ask this for any general connected linear algebraic groups. So the answer is no. This is again due to Polyethylene, Parimala, and Suresh. They provided a counterexample for this, and the counterexample was actually norm to right. So however, they in the same paper they also proved the following result, which is if we have a kappa which is algebraically closed field of characteristic 0, and we consider this field here, Lorentz series over that, and then function field over P1 over that. So then they proved that if we have a Galois extension with Galois groups Z mod 2Z cross Z mod 2Z, then the local Google principle holds. They actually proved a more general statement, to which I will come, which will appear later. Now at this point we can ask following questions. So what happens if we allow more general residue fields? And what if you consider more general Galois extensions? Their Galois extension was just Z mod 2Z cross Z mod 2Z. So what about more general ones? And what if we consider multinorm tori? So now I can mention the results. So let kappa be an algebraically closed field. So you can just think of complex numbers if you like. Let F be this semi-global field here, and let L over F be a Galois extension, and T sub L over F is the norm on torus. And we prove that if we assume that, sorry, you shouldn't take algebraic kappa to be complex numbers. We are allowing even other characteristic actually. So assume that characteristic of kappa does not divide this degree of the extension, then the local group principle holds. Yeah, so this is clearly a generalization of the previous result I mentioned. And for example, we can start with finite field of p elements, take its algebraic closure, and then consider this field here. Then if you take any Galois extension of degree n, which is co-prime to this p, then the local group principle holds. And now let kappa be an algebraically closed field, and again we are using this semi-global field. So for multinorm tori, if you consider quadratic cyclic extensions, some finitely many such extensions, and then if you assume that the characteristic of kappa is different from 2, then the local group principle holds for the corresponding multinorm torus. And in another direction, so suppose we have L1, L2, 2 degree p cyclic extensions, and assume that characteristic of kappa is different from p, then the local group principle holds for multinorm torus T sub L over F. So for 2 we can for p equals 2 we can say more, but for general p we are just taking 2 extensions. Okay, so these theorems actually can be generalized, so which we discuss now. So to these semi-global fields, actually we can associate a graph. So I'll just mention this briefly. So the thing is, so since this F is a function field of a curve over complete discretely valued field, so we can actually choose a nice model. So choose a regular proper model for this field, and then if you look at the spatial fiber, then we can look at the dual graph associated to it, and so that is the graph actually we are talking about. So whether this graph has loops or not, that does not depend on the model we choose. So this is an invariant of this field F. So whether this graph is a tree or not it just depends on the field F, and it plays an important role in studying local group principle for this tori. So so this condition didn't appear before because we are considering function field of P1, and for that the associated graph is a tree, which means it has no loops. So okay. So now I can talk about the general results. So let K be a complete discretely valued field with residual field kappa, and let F be a function field of a curve over K. So here I'm allowing more general curves. Assume that kappa is an algebraically closed field of characteristic 0. So here just think of complex numbers. Now, so Kolyothaler, Parimala, and Suresh actually proved this this thing, that if L over F is a Galois extension with Galois group Z mod 2 cross Z mod 2, and if you assume that the graph associated to F is a tree, then the local group principle holds. So this is always true for when the curve is P1. So that's why we had the previous result. And so similarly, we have general results for multinorm tori and Naumann tori and multinorm tori. So again, we have the same setup. So the result is let kappa be algebraically closed, or we are also allowing a finite field containing nth roots of unity, where n is the degree of the extension, this L over F. assume that the characteristic of kappa does not divide this number n, and suppose the graph associated to f is a tree, then the local global principal holds. And similarly for multinorm tori, we have similar statement. Assume that the residual field is algebraically closed, and we have some extensions, quadratic, cyclic. If the characteristic different from 2, and if the graph associated to f is a tree, then we have the local global principal. And a little bit surprising thing is that for the case of 2-degree p cyclic extensions, we do not need this tree condition. We just have this statement that if we have algebraically closed field and kappa, and L1 and L2 are 2-degree p cyclic extensions, if we assume the characteristic of kappa is different from p, then the local global principal holds for this multinorm torus. So this is all what I had to say. Okay, so a quick example, sorry. So we can take this field over complex numbers, and if you take any curve and take the function field over this, and for any 2-degree p cyclic extensions, the local global principal holds. So, and yeah, this is all what I have to say. Thank you very much for your time. Thank you.
Thank you, Sumit. So let's thank Sumit for a very nice talk. Are there any questions?
Yeah, Sumit, you mentioned about linearly disjoint extension, some result of
Yeah.
So can you recall that quickly?
Yeah, okay.
Uh,
Yeah, if you have two extensions, Galois extensions, which are linearly disjoint, so over a number field, then the local global principal for the corresponding
so don't you
multinorm.
need for individual extensions to the norm principle should hold for individual ones?
Oh, they are cyclic extensions, so it
Oh,
always
cyclic
holds.
extensions. Okay,
Yeah,
okay,
yeah.
okay. Okay.
Yeah. Oh, yeah. That is.
But then
that is,
what happens if I have for L1 the principal holds and for L2 it holds and they are linearly disjoint? Then can one conclude for the product? Is there a result of that sort? Am I clear about the question?
Yeah. You are saying that for the individual ones, the norm on tori, the principal holds, then does it hold for the?
Yeah, in other words, what you mentioned, more general version of the same result, I think. Without cyclicity, just assume that the principal holds for individual extensions, and then you want to conclude for the compositum or whatever.
I don't think that is all.
That's not true.
Any general result like this.
I see.
Yeah.
Okay. Thank you.
Yeah. Thank you.
Hi, Sumit.
Any other question?
I have.
Anything known about cohomological dimension of such fields?
I'm not sure. What would you expect to? Is it? Oh, no, but actually we are allowing base to be anything, right? So you have to fix this residue field first, then only. Right? In general, we cannot. Yeah.
Okay.
So, Sumit,
Yeah.
there is some known result or something for Henselian valued fields, not necessarily complete discrete number field.
You mean in the definition when I'm taking completely discrete valued, you are saying if you just take Henselian? Yeah, I don't think there is anything like this, like in the literature. I am not aware of, but yeah, I think something can be done even in that case. Yeah, that should be a nice thing if one can work out, replace complete discretely valued with just Henselian. Yeah, I've thought a little bit about that, but I have not done anything.
Thank you.
Thank you.
All right, let's thank Sumit once again, and let's thank him first, and then I'll introduce the next speaker. So our next speaker today is Gurleen Kaur. Gurleen, do you want to start sharing your slides?
Yes, sir. Yeah, okay.
Yep. So our next speaker is Gurleen Kaur today, and she's going to talk on the algebraic structure of rational group algebras from classical to modern approach. Over to you, Gurleen.
Thank you, sir. First of all, I would like to give thanks to Professor Manoj Kumar Yadav and Dr. Anupam Singh for organizing Group Theory Sangam series. It was a nice platform to interact and attain knowledge in diverse fields of this area. And I'm also thankful to the organizers of this conference for giving me an opportunity to present my research work. So starting with group algebra, throughout here G denotes a finite group. By Fg, we denote the set of all finite F linear combinations of the elements of G. The operations in F and the group G, it induces a natural sum and product in Fg through component-wise addition and multiplication defined via multiplication in G and distributively. This turns the set Fg into a ring. Since F is a field, Fg is an F algebra, and Fg is called the group algebra of G over F. So semi-simple group algebras, they are characterized by Maske's theorem. A ring is said to be semi-simple if it is a direct sum of finite number of minimal two-sided ideals. The group algebra Fg is a semi-simple ring if and only if the group G is finite and order of G is not a multiple of the characteristic of F. In other words, the order of G is invertible in F. This is a consequence of Maske's theorem. And these unique minimal two-sided ideals of Fg in the decomposition, they are called the simple components of Fg. So suppose Fg is written as a direct sum of simple components, then each simple component Ai, it is generated by a non-zero central idempotent, say Ei of Fg, where Ei satisfies the following. The distinct Eis are mutually orthogonal. The sum of all these Eis is 1, and Ei further can't be broken into two non-zero central mutually orthogonal idempotents. This set of idempotents are called the primitive central idempotents of Fg, abbreviated as the PCIs of Fg. Darwin and Artin provided a theoretical description of these simple components. Each simple component is isomorphic to a matrix algebra over a divisor ring, where the divisor ring is a finite dimensional division algebra containing an isomorphic copy of F in its center. This decomposition of Fg as a direct sum of matrix algebra over divisor ring is known as the Darwin decomposition. It was proved by Artin in 1927, generalizing the original work of Darwin done in 1908. Though it is a theoretical description, it's not a precise description. It doesn't provide us the knowledge about the Ni's, about the Di's. So a fundamental problem in group algebras, it is to explicitly determine the complete algebraic structure of a given semi-simple group algebra. That is, its complete set of primitive central idempotents and the precise Darwin decomposition. The problem is of great interest due to its links to various other problems in groupings. For instance, in the study of the unit group of the integral grouping ZG, the Darwin decomposition of the rational group algebra QG, it encodes information of the unit subset, and it plays a vital role in understanding the large subgroups of the center of the unit group of ZG. Then the next problem is isomorphism problem, which was imposed by Hickman in his PhD thesis in 1940. After that, several researchers gave positive answer to this problem for certain classes of finite group. And it was only in 2001 when Martin Hertwig provided a counterexample of a nilpotent by nilpotent group of even order. And this work is published in Annals of Mathematics. But still, the problem is of interest to look at the classes of finite groups for which the conjecture holds. The next one is the error correcting codes. And then there are other problems too, like the study of the normalizer problem, the study of the Jason-Horst conjecture, and many more. So once we have seen its impact on various other problems in group trees, we are interested in understanding this fundamental problem. So the classical way of determining primitive central idempotence, it was given by Toshiko Yamada in 1974. To compute the primitive central idempotent of the semisimple group algebra Fg, the first step is that compute the primitive central idempotence of the group algebra F bar G, where F bar denotes the algebraic closure of F using the character table of G, and then compute the primitive central idempotence of the group algebra Fg using a group action. But the known methods to compute the character table of G, they are very time consuming. Moreover, we have to compute the Galois group of Fi over X. So due to its limitations in practical applications, one is interested to look that whether we can determine the primitive central idempotence completely from within Fg, that is without any computations in the Galois group of Fi over F. A standard way of constructing idempotence from subgroups is that if I have a semisimple group algebra Fg, then this H hat is clearly an idempotent of Fg, where H is a subgroup of G, and H hat is central idempotent if and only if H is a normal subgroup of G. So in case H is a normal subgroup of G, we have a central idempotent of Fg. This again leads to a question that is it possible to obtain the PCIs of Fg from the subgroup structure of G? And then the researchers started working in this direction. Segal in 1970 proved that every PCI of the rational group algebra QG, it can be expressed as a Z linear combination of the standard idempotence. Then Jesper-Seal and Millis were able to provide an explicit description of the PCIs of QG for finite abelian group. Then the work was done for certain metacyclic groups. After that, in 2003, Jesper, Leal, and Peaks provided an explicit description of the PCIs of QG for finite nilpotent group G completely in terms of the lattice of subgroups of G. And to extend this work further to abelian by supersurvivor groups, soda pairs were introduced by Oliveri, Gergio, and Simon. Then they were able to provide an explicit description of the complete algebraic structure of rational group algebra of abelian by supersurvivor groups. On the other hand, the work was being done for understanding the complete algebraic structure of semi-simple finite group algebra of the same type of classes. In 2017, we provided an explicit description of the complete algebraic structure of rational group algebra for groups in class C of monomial groups, where C is the class of all finite groups whose each subquotient is either abelian or contains a non-central abelian normal subgroup. Then in 2019, we provided an explicit description of the complete algebraic structure of rational group algebra for generalized strongly monomial groups. And then we also looked at understanding the explicit description of the complete algebraic structure of semi-simple finite group algebra. These two works are published in Journal of Algebra, and this is in the finite fields and their application. So now to understand this class of generalized strongly monomial groups, the first step is to introduce the notion of soda pairs, which was introduced by Oliveri, Gergio, and Simon. A group is said to be a monomial if each of its irreducible complex character, it is induced from a linear character of some subgroup. And it's a very large class of survivor groups. In fact, every finite survivor group, it can be embedded in a monomial group. Oliveri, Gergio, and Simon, they introduced the term soda pair of G, which is a pair of subgroups of G in which the following conditions hold. And they were able to rephrase the Soda's theorem in terms of subgroups of G. Soda's theorem states that if you take a linear character xi on a subgroup H of G with kernel K, then the induced character xi induced to G is irreducible if and only if the pair H comma K is a soda pair of G. So now what is going to happen is that by this definition of soda pair of G, they were able to rephrase the theorem. We can easily see that through these conditions, it follows that the induced character will be irreducible if and only if the pair H comma K is a soda pair of G. So for finite monomial groups, soda pairs is sufficient to be able to conclude all the primitive central idempotents of the rational group algebra. To go further in this direction, some notations are to be introduced. Let K be a normal subgroup of H, which is a subgroup of G. Define H hat as stated. Epsilon HK, which was the main ingredient given by Jaspers, Leal, and Pates, while understanding the algebraic structure of rational group algebra for finite nilpotent groups. And EGHK is the sum of all the distinct G conjugates of epsilon HK. Now, clearly, EGHK being the sum of distinct G conjugates is a central element of QG. And once the distinct G conjugates happen to be mutually orthogonal, then EGHK becomes a central idempotent of QG. So this leads one to think that whether for a soda pair HK of G, EGHK, or a rational multiple of it becomes the PCI of QG. And this is exactly what O'Leary, Gervio, and Simon proved. Now, what they're more interested is that when is alpha 1, that is, when does EGHK becomes the PCI of QG? For this, they introduced the term strong soda pair of G, which is a soda pair in which further two constraints are there. And they said that the group G is strongly monomial if each of its irreducible complex character, it is induced from a linear character of some subgroup H of G with kernel K, with HK being a strong soda pair of G. They proved that if HK is a strong soda pair of G, then EGHK is a PCI of QG. A beautiful thing is that they were able to provide an explicit description of the complete algebraic structure of rational group algebra QG for a strongly monomial group G. So in particular for abelian by superseverable groups. What we have done in this direction is that in the paper, A Generalization of Strongly Monomial Groups, published in Journal of Algebra, we provided an explicit description of the complete algebraic structure of rational group algebra QG for a generalized strongly monomial group G. And since in this paper we were able to provide an extensive list of groups which are generalized strongly monomial, we were interested to look at how near is this class to the class of monomial groups. So we look at the properties related to it in this paper, which is available at arXiv and is submitted for publication. We revisited Dave's embedding theorem, which states that a finite severable group can be embedded in a monomial group, and proved that the embedding is indeed done inside some generalized strongly monomial group. We proved that supermonomial groups are generalized strongly monomial, which raised some interesting questions bigger than those asked by Isaacs in their investigations, and we will look at it. So to introduce the terms generalized strongly monomial groups, we first of all generalize the notation of EGHK. Let K be a normal subgroup of H, and let this be an arbitrary chain of subgroups of G. Set epsilon naught HK equal to epsilon HK. Epsilon 1 HK as a sum of all the distinct H1 conjugates of epsilon naught HK. So it is actually E H1 HK. Now again do the process. Epsilon 2 HK is a sum of all the distinct H2 conjugates of epsilon 1 HK. The final step we will obtain epsilon n HK, which is a sum of all the distinct Hn conjugates of epsilon n minus 1 HK. And we denote this by E frank G HK. So a soda pair HK of G, it is called a generalized strong soda pair of G. If there is a chain of subgroups of G from H to G called strong inductive chain, such that at each step the following conditions hold. Hi is normal in the centralizer of epsilon I HK in Hi plus 1, and the distinct Hi plus 1 conjugates of epsilon I HK are mutually orthogonal. Clearly, all the strong soda pairs are generalized strong soda pairs, because if you have a strong soda pair, say HK of G, then we can take the strong inductive chain H equal to H naught, subgroup of H1 equal to G, and then these two conditions are clearly satisfied because it tells the definition of strong soda pair. A group G is called generalized strongly monomial if each of its irreducible complex character, it is induced from a linear character of some subgroup H of G with kernel K, with HK being a generalized strong soda pair of G. So it's a generalization of strongly monomial groups, and it's sitting between the class of strongly monomial groups and monomial groups. But then we are interested to look at which are the other classes of groups which are generalized strongly monomial. So this picture tells actually that there is an extensive list of groups which are generalized strongly monomial. The groups in which each subquotient is either abelian or has a non-central abelian normal subgroup, they are generalized strongly monomial. This class was studied by Bertram Huppert, And eventually, many other interesting classes of groups can become generalized strongly monomial, like the subnormally monomial groups, which contain monomial Frobenius groups, Kamina groups, then the Survivor groups with all its Silo subgroups abelian, extended by super Survivor groups, and many more classes of groups. Now we understand the primitive central idempotence. So we take a generalized strong soda pair HQ of G, then E frank G HK is a primitive central idempotent of QG. And this construction of E frank G HK is independent of the strong inductive chain from H to G. So it means that if we have a generalized strong soda pair, we take any strong inductive chain from H to G, we compute E frank G HK, this turns out to be a PCI of QG. Then repetitively using this technical proposition, we obtain the simple component of QG associated to the generalized strong soda pair HQ of G, which is obtained in terms of the iterations of the cross products and the matrix strings. And this works very well for certain classes of groups, since the strong inductive chain is seen to be of length at most 4. Now, once we have seen this, we are interested to look at that how big is this class, how near is this class to the class of monomial groups. So firstly, we looked at Dave's embedding theorem. Dave's embedding theorem states that every finite Survivor group, it can be embedded inside some monomial group. And this you can find in the book of Bertram Huppert, because it was an oral communication by Dave to Bertram Huppert. So it is available there. And the key step in the proof of this theorem is that given a finite Survivor group G, you consider a subnormal series with factor groups of prime order. We can do this by taking a maximal normal subgroup in the group G, it is of prime index. Then again, take another maximal normal subgroup in that group, and you will obtain a subnormal series chain with factor groups of prime order. And we denote the factor group by Ci. So the crucial steps were that G is isomorphic to a subgroup of certain ret products by cyclic groups, and the ret product of a monomial group by a cyclic group of prime order is monomial. So what we have done is we have proved that this embedding, it is actually indeed inside generalized strongly monomial groups. So every finite Survivor group can be embedded inside some generalized strongly monomial group. And the key steps in the proof were that the ret product of a generalized strongly monomial group by a cyclic group of prime order is generalized strongly monomial, and a finite direct product of generalized strongly monomial groups is generalized strongly monomial. So we will easily get this result then. Now, the next thing which we proved is that supermonomial groups are generalized strongly monomial. For that, I have to introduce the term compound Clifford correspondent and the stabilizer limit. It was given by Isaacs in 1986. So you take an irreducible character in a group G, take a normal subgroup of the group G, and take an irreducible constituent of the restriction of chi to n. Then you take the inertia group of theta in G. And so by Clifford's correspondence theorem, we know that there is a unique Clifford correspondent psi of chi with respect to theta, such that chi is induced from xi. Now we can repeat this process. Now we take a normal subgroup in T, we take the restriction of xi to that normal subgroup, take its constituent, take the Clifford correspondent, and again you do the same process. This iterative process can be continued. So a character xi obtained through any number of such iterations is called a compound Clifford correspondent of chi. And at the end, when you're not able to go further down, means you're not able to find further any Clifford correspondent, or in other words, we can say that that's a quasi-primitive character. But since we are dealing with solvable groups, it means that it's a primitive character. So when we reach at the primitive character, at the stage of primitive character, then they are called the stabilizer limits of chi. So we proved that supermonomial groups are generalized strongly monomial. Supermonomial groups are those groups in which every irreducible complex character is supermonomial. In other words, it means that if I have an irreducible character in a supermonomial group, say chi, then every primitive character inducing chi, it is linear. This property doesn't hold generally in monomial groups. So how we prove that supermonomial groups are generalized strongly monomial? We use the same process. We are able to see from this that we have a chain from a primitive character to that character. We have a chain, chi is getting induced from a primitive character. And since the group is supermonomial, that primitive character must be linear. And we prove that that chain is actually turning out to be a strong inductive chain from that subgroup, say H to G. and therefore that becomes a generalized strongly monomial character. And since each character is generalized strongly monomial, the group turns out to be generalized strongly monomial group. Now, why we are interested in understanding this supermonomial groups, the reason is that the conjecture is the people are interested, the researchers are interested in understanding the subgroups of the monomial groups, that whether the normal subgroups of monomial groups are monomial. The first question which was imposed was that whether the normal whole subgroups of monomial groups are monomial, and John Hoff in 1967, he proved that yes, normal whole subgroups of monomial groups are monomial. And then the question was raised that whether the normal subgroups of monomial groups are monomial, then they was able to find a counterexample for monomial groups of even order. He was able to find an example of order 2 raised to 9 into 7, and where there is a normal subgroup of index 2 in the group, which is not monomial. But the question was still open for the groups of odd order. So the question was that whether the normal subgroups of monomial groups of odd order, they are monomial. And Isaac said in his paper, he said in 1994, that the problem with working with monomial characters is that every primitive character inducing that monomial character, it need not be linear. So therefore, he introduced the term supermonomial characters, in which this is the property, that every primitive character inducing that character is linear. And he said that once we show that every monomial group of odd order is supermonomial, there are positive instances which says that we can prove this conjecture that every normal subgroup of monomial group of odd order is monomial. And in fact, Lewis in 2010, he proved that yes, if this conjecture holds true, that every monomial group of odd order is supermonomial, then we will be able to prove that normal subgroups of monomial groups of odd order are monomial. So now, once we have seen that supermonomial groups are generalized strongly monomial, we can ask a weaker conjecture that whether every monomial group of odd order is generalized strongly monomial. This will not only help us in further understanding the explicit description of the complete algebraic structure of rational group algebra, which is of great interest for group ring theorist researchers, but also for the group theorist researchers. Maybe it will give some positive instance to answer this question that every monomial group of odd order is supermonomial. And maybe if we can answer another question that if every generalized strongly monomial group of odd order is supermonomial, then yes, if these two questions will hold, then of course this conjecture will be proved that every monomial group of odd order is supermonomial. So therefore, an affirmative answer to this question will be of great interest for grouping theorists as well as for group theorists. So this completes my talk. So thank you so much.
Thank you, Gurleen. Other questions? So questions from the audience, please. Hello. Am I audible?
Yes, ma'am, you are audible.
If there are no questions, let's thank the speaker again. So our next speaker is Koma Patali.
Yes.
Yeah, she is from ISER Trivendrapuram. Koma Patali.
Yeah. Okay. Okay. I try my share, like screen sharing. Okay. Ma'am, should I begin the talk now?
Yeah, please. Over to you.
Okay. Okay. Thank you. Uh, Thank you, ma'am. And also, I would first like to thank Group T the Sangam Talks also for the Group T the Sangam conference. And today I am presenting a proof of a property of P groups having nilpotency class at most P plus 1. Uh, Also, I mentioned that the theorem which I am presenting, it's a joint work with Ammo Antony, also with my advisor VG Thomas. So uh, first we recall a well-known theorem of Schur, which says that let G be a group if the central quotient G mod center G is finite. That is, if center G has finite index in G, then the commutative subgroup gamma 2G is finite. Also, people studied theorems which are similar to this theorem, that studying the property of gamma 2G in terms of an analog property of G mod center G. In order to study, also first we state Schur's exponent problem. The problem asks whether or not a given finite P group satisfies equation 1. The equation 1 asks exponent of second homology group H2GZ. Does it divide exponent G? So it is known as like Schur's exponent problem. And to see a relation of Schur's exponent problem with a theorem like Schur, we first recall what is a covering group of a group G. Let G be a group. A covering group is a central extension where the Z is a central subgroup. Z is also contained in gamma 2A, and such that Z is isomorphic to the second homology group H2GZ. This homology group is also called as Schur multiplier. Now, suppose if you prove exponent of gamma 2H divides exponent of H mod center H for the covering group H of G, then it follows that equation 1 holds for G. So suppose if you want to prove equation 1, there are several approaches. One such approach is consider the covering group of G and prove equation 2 for the covering group, for a covering group. Then equation 1 follows for G. Our main theorem is we will prove equation 2 in a P group of nilpotency class P plus 1. And as a consequence, we will get through the Schur's exponent problem for a finite P group of nilpotency class at most P. And before going to the theorem, we will make some remarks, like we recall about validity of equation 1. And it was disproved that equation 1 for the group, that is, in 1974, the first counterexample to equation 1 is constructed. The group is a 2 group having order 2 power 68 and nilpotency class 4, such that exponent of G is 4, but exponent of the H2GZ is 8. So equation 1 is not valid for this particular group. Later, equation still remained open for groups having odd order, but recent counterexamples constructed by Professor Wagenly, which shows that there are groups of odd order also where the equation 1 fails. He constructed a group G of order 5 power 4122 with nilpotency class 9. Also, the group has exponent 5, but the exponent of Schur multiplier is 25. Also, he constructed a group G of order 3 power 11,983 having nilpotency class 9 with exponent G is 9 and the exponent of Schur multiplier is 27. So equation 1 is not valid for this group also. Now, there are some instances or some classes of groups where the equation 1 is proved. It was proved by M.R. Jones that the equation 1 is true for groups of nilpotency class 2. Also, a finite P group G is powerful either if P is odd and gamma 2G is contained in GP, or if P is 2 and gamma 2G is contained in G4. It was proved by Lubarsky and Mann that equation 1 is holding for powerful P groups. Also, a finite P group G is potent if gamma P minus 1G is contained in GP. And it was proved by Moravec over various papers that equation 1 holds for meta-abelian P groups of exponent P. He also proved equation 1 for groups of class at most 3 and groups of class at most 4 and of odd order. Also, P groups of class at most P minus 2. Also, equation 1 holds for 3 Engel groups, also 4 Engel groups with exponent V, where E is not divisible by 2 or 5. Furthermore, equation 1 is also proved for P groups of maximal class, also for potent P groups. And for P groups of nilpotency class 5, Moravec proved that exponent of Schur multiplier divides exponent G square. Also, equation 1 is proved for finite groups with nil commuting probability greater than 0.25. Moreover, the result of Moravec says that if the group G has nilpotency class at most P minus 2, then equation 1 holds for G. And it was proved by Masayeki et al. That equation 1 holds for finite P groups of class at most P minus 1. That is, they extended equation 1 for one more nilpotency class. And it is our recent work, we have proved the equation 1 holds for finite P groups of nilpotency class at most P. Also, our result involves finite P groups of nilpotency class 5 with P is an odd prime. Also for P central meta-abelian P groups, as well for finite P groups satisfying the condition that gamma PG is contained in GP square. Now, we will obtain all these results as a consequence of one theorem, which I denote as theorem 1 in this presentation. Before stating theorem 1, let us recall a lemma proved by Mann that let G be a P group of nilpotency class at most P. Let X comma Y be 2 elements of G. Then the 3 conditions that commutator X comma Y Pn is 1, which is equivalent to commutator xy having order P power n. And similarly, these two are equivalent to X power Pn will commute with Y. And also, I make a remark that this theorem, this lemma is actually given by Mann for the case where Pn is equal to P. But the same argument will hold for a very natural number n. And as a consequence of the lemma, we've obtained that if a P group G is having nilpotency class at most P, then exponent of gamma 2G divides the exponent of G mod center G. And as a consequence, we can get that suppose if G is a P group having nilpotency class P minus 1, then its covering group being a central extension of G will have nilpotency class at most P. And as a consequence of this lemma, equation 2 holds for covering group of G. And that yields equation 1 for group G. So the result that the equation 1 for groups of class at most P minus 1 follows as a consequence of the lemma of Mann. And in theorem 1, we proved that we extended this result to one more class, that let P be a prime and G be a P group if the nilpotency class of G is less than or equal to P plus 1. Then exponent of gamma 2G divides exponent of G mod center G. That is equation to prove holds for all the P groups of nilpotency class at most P plus 1. And before going to the proof, we set up our notations. All our commutators are left now. Also, commutator xy denote x inverse y inverse xy. Now let G be a P group of class P plus 1. Let exponent of G mod center G is P power n. Our aim is to prove every element of gamma 2G has order dividing P power n. And before proceeding that, we make an observation that G has class at most P plus 1 and hence gamma P plus 2G is 1. And this will yield that gamma 2G will have nilpotency class at most P minus 1. Thus gamma 2G will be a regular group. So if you have a product of elements in gamma 2G, order of this product will be less than or equal maximum of order of elements involved in the product. And hence, to prove exponent of gamma 2G is P power n, it is sufficient to prove that every generator of gamma 2G has order dividing P power n. So we prove that commutator xy P power n is 1 for all x comma y in G. And after few steps, like we came across that commutator, because xpn is in center G, commutator xpn comma y will be 1. And we will expand the commutator xpn comma y. And after the expansion and after some intermediate steps, we deduce that commutator xy power pn is equal to y comma commutator px, where the x is appearing p times power pn choose p. Also, here I would like to remark that if you have pn choose r, where r is at most p minus 1, then pn will divide pn choose r. But instead of r less than p, here we have that pn choose p. So the maximum power of pn dividing this pn choose p will be p power n minus 1. But we are going to show that this commutator is having order p power n minus 1. So our sketch of I will give a sketch of how we showed this commutator is 1. That I will explain my proof with an example. Let G be a 5 group where my P is 5 and my group has nilpotency class P plus 1, which is 6. And let exponent of G mod center G be 5 power n. Now we set up some notations. Let S x comma y denote the set of all commutators of the form commutator y x c1 c2 c3 c4 such that each ci is either x or y, and S of x comma y denote set of all such commutators. Also, all these commutators are having weight 6, and gamma 6G is contained in center G because nilpotency class is 6. So each element of Sxy commute with one another because they all are central elements. Now we define ER x comma y. Let ER x comma y denote the product of all the commutators from Sxy having weight r plus 1 in y. That is, each of them they have y. Also, we demand r of c1, c2, c3, c4 to be y. Thus, the commutator will have weight r plus 1 in y, and this r varies from 0 to 4. Because none of the ci could be 0, or all of the ci could, none of the ci could be y, or all of the ci could be y. So now we observed that suppose you take an element in S of xy comma y. The element looks y comma xy comma c1 c2 c3 c4, where each of the Ci is either xy or y. And this commutator is equal to y comma x comma c1 c2 c3 c4, and we can expand this commutator and we can make it as a product of commutators where each of these positions is either x or y. So that we say that W can be written as a product of elements in Sx comma y. Also, moreover, we had an observation that in doing this product, suppose if you take et xy comma y, that is product of all the commutators having t plus 1 weight in y. When you expand et xy comma y, you will get that product es x comma y raised to s choose r, where s is from t to 4. This was a crucial observation which helped in our proof. Having this observation, we proceed to with our example, noting that xy power 5n is equal to xy by 5 power n, but equation 3 says that commutator xy power 5n is equal to y comma 5x 5n choose 5. Also, xy by power 5n is equal to y comma 5 times xy. That is same as commutator y comma x comma 4 times xy power 5n choose 5. And using, we will expand the right side of this equation using equation 4. That is, it is saying that E0 of x comma y is equal to E0 of xy comma y raised to 5n choose 5. But E0 of xy comma y is equal to the product E1, E2, E0, E1, E2, E3, E4. And on cancelling the E0 of x comma y on both sides, we get that E1, E2, E3, E4 of x comma y raised to 5n choose 5 is 1. This is, we number it as equation 5. And applying equation 5 is valid for every x comma y in G. So we apply equation 5 with xy comma y, or in other words, we replace x with xy in this equation. Further, we expand the resultant equation that has E1 xy comma y, and that can be written as EI x comma y using equation 4. So the resultant equation will be this, because this is the replacement of E1 xy comma y. The next is the replacement of E2 xy comma y, and E3 xy comma y, and E4. And we compare equation 6 with equation 5. That will yield the E1, E2, E3, E4 of x comma y 5 and choose 5 is 1, and hence the remaining product will be 1. Also, all these elements, they commute with one another. So collecting the powers together, we've obtained that E2 square, E3 6, E4 14 of x comma y, 5 and choose 5 is 1. Similarly, we repeat the same process with equation 7. That we replace x with xy in equation 7, and we expand that equation, and we compare the resultant equation with equation 7. And finally, that will yield the equation 8, which says E3 power 6 and E4 36 is of x comma y is 1. Again, we repeat the same process with equation 8. That is, we replace x with xy in equation 8 and we expand it, and we compare the resultant equation with equation 8. As a consequence, we obtain that E4 power 24 x comma y 5 and choose 5 is 1. And G is a P group, and 24 is relative. G is a 5 group, and 24 is relatively prime to 5. And hence equation 9 gives E4 x comma y 5 and choose 5 is 1 for every x comma y. Moreover, we see what is E4. E4 is the product of all the commutators y comma x comma c1, c2, c3, c4, such that the total weight in y is 5. So E4 contains only one commutator, and that is this. And we take the E4 inverse. E4 inverse become commutator x comma 5 times y. Then equation 9 gives that E4, thus we will obtain that x commutator x comma 5 times y power 5 and choose 5 is 1. And it holds for every x comma y in G. This is what we observed with this example. Now, suppose if you work in a general P group you of class P plus 1, we deduce that commutator y comma px power p and choose p is 1 for all x comma y in G. That is, we can replace x with y in equation 10, or we can interchange x with y in equation 10. That will give commutator y comma 5 times x. This commutator power 5 and choose 5 is 1. So that is what we obtain. Then our equation 3 is commutator xy pn is equal to this commutator, which is 1. And hence we obtain every commutator x comma y has order dividing p power n. And as we observed before, it proves that exponent of gamma 2g divides p power n. Hence this proves the theorem. And as a consequence of the theorem, we get that Schulze exponent problem holds for every finite P group of nilpotency class at most P. And here I would like to stop. Also, I will mention what is the further research possible in this direction. One can study groups with small nilpotency class. Say groups having nilpotency class at most 8. Does the Schulze exponent problem holds? Because the counterexamples given were of nilpotency class 9. So the Schulze problem is still open for groups of odd order nilpotency class 8. And because the nilpotency class is small, it can be again attained, like we can attempt the problem using the commutator calculations. Also, there are some problems regarding meta-abelian groups, also regarding the Engel conditions. So one can work in that directions also. And thank you for, these are my references. And thank you for attending the talk.
Thank you, Koma. So now I invite questions from the audience.
I have a comment.
Yeah.
Yeah, I think I have brought some time ago that if G is a P group of class P, the exponent of the commutator subgroup is equal to the exponent of G over the center.
G over the center.
I think I used less machinery than that.
Yeah.
So I mean that you may find useful things in my argument.
Yeah.
Yes, I proved more. If every element in the P center, in the Pth lower term of the lower central series of J is fixed by J, then the exponent of the commutator and the central quotient are equal.
Yeah.
Do you understand? I could give you the paper. Okay. Thank you.
Okay.
You would use less machinery than more conceptual argument.
Yeah.
Okay, thank you.
Yeah. And like I gave this consequence because our main theorem is in these lines. Our main theorem is proving the same statement for one more nilpotency class.
Yes, yes, this is stronger, but you may use the arguments, the tools I have used it to improve the proof, perhaps, or probably.
Okay, sir. Okay, sir. Okay.
Any other question? Can you show your problem one? You said equation one at various places.
Yeah, equation 1 is the
This is your equation one. Okay, the exponent actually.
yeah exponent divides.
Sure, exponent problem.
Yeah.
Okay, any other question?
Another comment.
Yeah.
Mrs. Patali,
Yes.
you proved that the exponent of h prime is equal to the exponent of the central quotient, or just divided?
Divides it.
In your proof.
In my proof, it will be equal to that.
Equal.
Yeah, my proof shows it will be
Equal.
It will be at most that. Yeah.
Equal for p groups of class p plus 1, at most p plus 1.
No, the proof says that exponent of gamma 2 of g
Equal
is
or just divide?
divide.
Your proof.
Yeah, my proof shows it will divide.
Okay. Do you have example where the it is a proper divisor? That is, you don't have the equalities.
Yeah, but I think you can take the example of a group of exponent 3. I mean the Gmod center G has exponent 3. And then you can prove that exponent of gamma 2 G is equal to 3 itself. I mean G be a non-abelian group such that Gmod center G has exponent 3.
Yes.
Then we will get the equality in this case.
Now I mean, do you have always the equality, or you have counter example that show that it just divided?
No, always in this case, always it will be equality because gamma 2h is non-trivial. So
no, I think
also
I mean for all p groups of class at most p plus 1.
No, I mean for 3 group where my p is equal to 3 and my group has nilpotency class 4 such that exponent of Gmod center G is equal to 3.
And the exponent of gamma 2?
Because gamma 2G is non-trivial. I mean, gamma 2G will be non-trivial because it's a non-abelian group. And we shows that its exponent is 3.
You have the equality.
We have the equality because it's non-trivial group. So we have the equality.
Sorry for taking your time.
Okay.
I mean, we can discuss this later. I mean, an example that shows that the exponent of gamma 2 is strictly less than the exponent of h over zh.
Okay. I think strictly less than is also possible, but I'm giving an instance where it will be equal.
Okay. Thank you.
Yeah, but strictly less than could be possible. Okay.
Okay, thank you.
Okay. Are there more questions? Okay, so if there are no questions, let's thank the speaker once again. So it's time for the coffee break. And let's meet at 4 o'clock, right? So I request everybody to join 5 minutes before the scheduled time. So let's meet at 3:55 so that we can start right at 4 o'clock. Okay.
Yeah. So as usual, there is a breakout room also. People can go to breakout room and do the chit chat. Those who wish to do in the
Okay.
meantime. Yeah.
There are many breakouts rooms you have created.
Just one.
Just one. Okay.
Yeah.
Good. Okay. So good evening. So it's a pleasure to welcome you all back after the tea break. So hope all of you are refreshed. So this is the last session of this conference, and the speaker of this evening, the first speaker of this evening is Ratan Lal from Central University of Rajasthan. He will talk on classifying gyrotransversals in groups. Ratan Lal, over to you.
Yes, thanks, ma'am. Hello. Hello.
Hello, yes, we can hear you. Yeah, you can start, Ratan Lal.
Okay, ma'am. I have to just. Yeah. Can I start, ma'am?
Yes, yes, please.
Okay. First of all, I would like to thank the organizers of Group Theory Sangam to allow me to speak in this program. I will talk on the classifying gyrotransversal in groups. In 2015, Al Gore and Militaru gives a classification of subgroups, complements of a subgroup in a group. So motivating from this, we are classifying gyrotransversal to a subgroup in a group. So first we will define some basic terminology that we will use throughout the talk. First is the definition of a loop. A loop consists of a pair. L within L is a non-empty set and dot is a binary operation on L, which satisfies two conditions that for any AB in L, the two equations x dot A equals to B and A dot Y equals to B have unique solutions x and y in L. And there is an element 1 in L which satisfies this condition for all x in L. Then we say that this is a loop. Note that a loop is a non-associative structure which satisfies all the properties of groups except the associativity. As an example, we have a loop of order 5 here. For non-associativity, we see that 1 into 1 into 2 is 4, but 1 into 1 into 2 is 2. So associativity is not there. Next is the definition of transversal to a subgroup in a group. Let H be a subgroup to a group G, and let us collect all the right cosets of H in G in a set. Then the set consisting of exactly one element from each right coset is called right transversal. If we take left cosets, then we say that it is left transversal of H in G. Now, let S be a right transversal to a subgroup H in G, which contains the identity element corresponding to the trivial coset H in G. And let us choose two elements X and Y in S. Then they represent two cosets Hx and Hy. So if we multiply the element xy and take a coset hxy, then taking that element from this coset which lies in S, then with this process we can define a binary operation circ on S such that the structure S comma O is a right loop with this operation O. Then in this paper, Ramjilal had proved that the group generated by the maps f of xy is actually subgroup of the subgroup H in G, which is called group torsion of S. And these maps f of xy are defined from S to S by the right action of H in S. The theta here is the right action of H on S. Then this S is also right transversal to the subgroup group torsion GS in the group generated by S. So here we see that all the theory depends only on the S. Now, in 2000, Fogel and Ungar introduced the notion of left gyro group and gyro transversal to a subgroup to a gyro group in a group. So in 2013, Ramjilal and Akhilesh Chandra Yadav studied the right gyro groups and gyro transversals. So we are taking the definition from this, that a pair S comma O, where S is a non-empty set and O is a binary operation on S, with right identity E and a right inverse A prime for every A in S, satisfying this equation, is called a right gyro group if for any three elements X, Y, and Z in S, there is a unique element X theta f of yz, which we defined in the earlier slide, in S, such that the equation, this one, is satisfied. Moreover, these maps f of yz from going from S to S are automorphism of S, and for any y in S, f of y comma right inverse of y prime is identity map on S. So from this equation, we see that the associativity is not there in this structure. So this right gyro group is actually a right loop. As an example, we have Mobius disk gyro group. So consider a unit disk D in the complex plane C with the Mobius additions big plus M. We see defined like this. We see that this set with this operation is not associative, but it satisfies all the properties of gyro group. So it is a right gyro group. Now, the gyro transversal, a transversal S to a subgroup H in a group G is called gyro transversal if it satisfies the three conditions. First, it contains the identity element of the group in the group G corresponding to the trivial transversal H of G, and inverse of every element of S is in S, and H normalizes S. It means for all H in H inverse SH is a subset of S. As an example, we have that symmetry group on three elements S3 and H be a subgroup of order 2. Then this is a transversal to H in G, which is a gyro transversal. Now, in 2000, Fogel and Ungar gives a representation theorem for right gyro groups. It states that a right loop S comma O is a right gyro group if and only if it is a gyro transversal to the group torsion GS in its group extension GSS. It means every right gyro group can be identified with a gyro transversal in some group. So the theory of loops can be transferred to groups. Now, we know that corresponding to a subgroup in a group G, there are lots of transversals. Then in this paper, Ramjilal and Akhilesh Chandra Yadav have given a structure to find all the algorithm to find all the transversal corresponding to a transversal. They state that if S is a transversal to a subgroup X in G, and then any other transversal will give a map G, and any map G defined in this way will give a transversal to a subgroup H in G, which is defined in this sense. So Now now we want to see that when will this transversal be a gyrotransversal. So if S is a gyrotransversal to subgroup H in G, then with this map, this set will be a gyrotransversal to H in G if the map G satisfies two more conditions, which is defined in 1 and 2. Then this new set SG will be called deformed gyrotransversal, and this map G will be called deformation map. Also, this set S with the original operation O is a gyrotransversal. So applying the original operation O on S induces the operation OG on S defined like this. Then with this new operation, this set S also forms a gyrotransversal, and it is observed in this paper that the two gyrotransversal corresponding to the map G are actually isomorphic to each other. Now we will classify the gyrotransversal to a subgroup in the group in a group. So for this, let us collect all the deformation maps in a set R and define a relation sim on R by any two maps are related to each other if and only if the corresponding gyrotransversals are isomorphic to each other. So which is given by the map tau here. Then it is easily seen that this relation is an equivalence relation on R. So let us collect all the equivalence classes of the elements in R in a set which is denoted as R mod sim, and the set of all isomorphism classes of gyrotransversal to the subgroup GS in the group GSS. Let us note this set by GYR, GSS, GS. Then our main theorem is, if S is a gyrotransversal to a subgroup GS in the group GSS, then these two sets defined here, these two sets are actually in 1-1 correspondence. So outline of proof is, let T be any gyrotransversal to the subgroup GS in the group GSS and O dash be the induced binary operation on T. Then as the proposition in the paper by Ramjila and Akhilesh Yadav, we see that any gyrotransversal is given by a deformation map G. So let this gyrotransversal T be given by a deformation map G, and this is equals to some SG. Then we see that this SG is actually isomorphic to the gyrotransversal with the deformed operation. Thus, we have a bijection map from the class of isomorphism class of gyrotransversals to the equivalence class of maps deformation maps. Stop. Now, as an application part, we will find the gyro isomorphism class of gyrotransversals to any subgroup in the dihedral group Dn. Let Dn define like this: the dihedral group of order 2n, where n is greater than equals to 3, and h equals to h be generated by y, a subgroup of order 2. Now we know that any subgroup of Dn is either a cyclic group or a dihedral type group, which is listed in these two listings. Now for any s in 0 to r minus 1, we can define a map phi from Dn to Dn defined in this way. Now it is observed from this map that this is an automorphism of Dn, which takes the subgroup K1, which is generated by xr and y, to any subgroup of the form xr xsy. It means it is sufficient for us to study the gyrotransversals only for the subgroup K1, as any other is isomorphic to this one. Similarly, the subgroup generated by y is taken to the subgroup y xj for some map phi. So we will find the isomorphism class of gyrotransversal corresponding to the three type of subgroups that we have discussed. First, we will use the subgroup H, then the cyclic type subgroup, and then the dihedral type subgroup. Now, first we will find the total number of gyrotransversals to a subgroup in Dn. So if we take the subgroup H, then the total number of gyrotransversal is given by this simple formula that if n is odd, then the total number of gyrotransversal is 2 raised to power n minus 1 by 2, and if n is even, then it is 2 raised to power n by 2. Next, if we take the cyclic type subgroup, then the total number of gyrotransversal is given in a very particular case here. This is the when R is n by 2 and it must be odd. Otherwise, there is no gyrotransversal in this case. And if we take the dihedral type subgroup, then the total number of gyrotransversals are given by this formula for two cases, n is odd and even. Now, Now we will find the isomorphism class of gyrotransversals corresponding to these subgroups in the group Dn. So in this paper, Fogel and Unger have given a very important result that if B is a gyrotransversal to a subgroup K in the group G, such that G is the product of this gyrotransversal and the subgroup K, then this B is also a gyrotransversal to the subgroup K quotient by centralizer of B in K in the group G quotient by centralizer of B in K. So if we can find the gyrotransversal corresponding to the subgroup K in G, then this will also the gyrotransversal to the quotient group K by centralizer of B in K and in the group G by centralizer of B in K. So using this result, we will prove that it is sufficient for us to find the isomorphism class of gyrotransversals for the subgroup H only. So now, first note that if we take the subgroup generated by XR, then it is a normal subgroup in Dn. Since it is a normal subgroup, so any gyrotransversal to the subgroup K in Dn as a right loop is actually isomorphic to a quotient group. So the gyrotransversals corresponding to this subgroup are unique up to isomorphism. So the number of isomorphism class is 1. Now, if we take the subgroup generated by x raised to power r and y in Dn, where r is not equal to n, then it is easily seen that s equals to 1, x, xi, xr minus 1 is the gyrotransversal of s of k in Dn. Then the centralizer of this s in k is given by the set 1, xr, x2r up to xn minus r. Now note that the order of k here is 2n by r and the order of this centralizer is n by r. So the order of this quotient is 2 and the order of g by g here is dn. So order of dn by centralizer is 2r, which is isomorphic to the dihedral group of order 2r. So we see that the isomorphism class corresponding to this subgroup is actually correspond to the isomorphism class of H in Dr. So it is sufficient for us to study the isomorphism class of gyrotransversals to the subgroup H in the group Dn. Now, so let T equals to 1 x, x square, xn minus 1 be a gyrotransversal to the subgroup H in Dn and G be a deformation map. Then we know that any gyrotransversals to H transversal to H in Dn is given by the set Tg, where G is defined from T to H by some power, some xi's are going to identity and some xi's are going to y. So if we take those components, those exponents of x which are going to y under G and construct a set B, then we see that this set B actually determines the map G. And in this paper by Vipul Kakkad and R.P. Shukla, they have proved that the group cyclic group of order n with the operation XOBY with the which is induced from the set B defined like this, then this group is actually a right loop with this operation, which we denote by this. Then we see that this right loop is actually a right gyro group if and only if for any I in Z and B minus I is also in Z and B. So corresponding to a map G, we have two gyrotransversals TG and Z and B. So we will identify every gyrotransversal to the with the set Z and B here, which is given by the isomorphism here. Now, before proving the finding the isomorphism classes, let us define some lemma. First, if G and H are any two members in R such that they are related, and Z and B, Z and A with the right gyro groups associated to the gyrotransversals TG and TH respectively, then note that G and H are isomorphic related to each other, so the gyrotransversal corresponding to these maps are isomorphic to each other. So the isomorphism between gyrotransversals actually gives the isomorphism between the right gyro groups Z and B, Z and A, by which is defined by any element A in Z and B is going to RA for some R in UN, where UN is the group of units of N. So here we see that the isomorphism of gyrotransversals can be identified with the multiplication action of UN on the set Zn. So from now on, we will identify the isomorphism of gyrotransversals with the multiplication action of UN on Zn. So let us collect a set corresponding to each proper divisor D of n, where by proper divisor I mean that D divides n and D is not equal to n. So we consider the set xd bar, which is all the multiples of D, where R is coming from U n by D. Then we have proved that this set xd bar is actually the orbit of this element D under the action of Un on Zn. Now, if we collect all these xd bars, and then we see that this collection actually forms a partition of the set Zn minus 0. And moreover, if there is some D prime which divides the cardinality of this set xd bar, then we get a subset of cardinality D dash in xd bar, which we denote by yd. And the stabilizer of this yd is 2 into D prime into order of stabilizer of xk, where xk is any element in yd. So this is very important lemma here. With the help of this lemma, we will find the isomorphism class as follows. Now, note that if we take any two elements A and B in Zn minus 0, and there is an element R in Un which takes A to B, then the corresponding gyrotransversals Zn-A and Zn-B are also isomorphic. So the choice of the maps G is basically the choice of the elements from the set B, and the choice of the set B is actually the choice of elements from the set xd bar. So we will so that isomorphism depends on the set selection of the elements from the set xd bar. So now in particular, if we take the set B as xd bar, then by orbit stabilizer theorem, we have that this stabilizer of this xd bar is Un. It means it is the gyrotransversal corresponding to the set B is unique up to isomorphism. So here D is the set of all the proper divisors of n. So corresponding to each proper divisor D of n, we get a gyrotransversal which is unique up to isomorphism. Now, also note that if I is in B, then by the inverse property of gyrotransversal, n minus I is also in B. So it is sufficient for us to study only the half of the elements of the set xd bar, which we denote by xd. Also, we see that if A stabilizes a gyrotransversal Znb, then the inverse minus A also stabilizes the gyrotransversal Znb. So again, it is sufficient for us to study the set small un, which contains exactly the half of the elements of the set un, capital Un. Now, we will find the isomorphism class of gyrotransversals in two parts. First, we will find the isomorphism class of gyrotransversals of H in Dn containing only one element, and then we will find the isomorphism class of gyrotransversal containing more than one element. So for one element, we have a direct formula that if the number of isomorphism classes of gyrotransversals of H in Dn containing only one element is 2 raised to power tau n minus 1, where tau n is the number of divisors of n. So outline of proof is, if D dash is the divisor is equals to the cardinality of xd bar, then by the third lemma here, we see that the stabilizer of xd is 2d dash into stabilizer of xk from any xk in xd. So which gives us that the stabilizer of xd is un. So it reflects that for any proper divisor D of n, we get a gyrotransversal which is unique up to isomorphism. Also, by orbit stabilizer theorem, we note that no proper subset of xt is stabilized by all of you. So combining these two things, we get that the total number of subsets of Zn minus 0, which are stabilized by all of un, is tau n minus 1, that is number of proper divisors of n, and all of their possible combinations. So which is given by the expression here. So which gives the required formula. Now, the number of isomorphism classes of gyrotransversals containing more than one element is given by the formula here, where this summation runs over all the proper divisors of cardinality of small un, and both of these sums run over all the tuples such that the GCD of stabilizer of each xij taken from distinct xtj is D. So this is very important point to note here, that we have to choose those tuples such that the GCD of stabilizer of each xi alpha is taken from each distinct xkj is always D. The D correspond to the divisor D which we are taking at a time. Now we have to understand all the process. We have given I've given an example here. So let D9 be the dihedral group of order 18 and H be a subgroup generated by Y. Then here note that N is 9. So the total number of gyro transversals is 2 raised to power 9 minus 1 by 2, which is 16. So there are 16 gyro transversals, and the corresponding to each gyro transversal we get a deformation map. So these are the 16 deformation maps, and each deformation map is determined by the set B. So these are the 16 B sets where B1 is empty set. Now to find the isomorphism class, first we find here U9, small u9 is 1 to 4, and the proper divisor of 9 are 1 and 3. So corresponding to 1 and 3, we have the sets x1 and x3, which are defined there, and x be the union of these two sets. Now, the the cardinality of small un is 3, and the divisor of 3 are 1 and 3. So there are two types of isomorphism classes of gyro transversals to H in Dn, containing one element or the 3 elements. So for the isomorphism class containing one element, we have by formula that that the divisors of 9 are 3. So the formula gives us the answer 4. Also, we can see directly from here that if we take the set B3 and multiply it by any element of U9, we get the set B3 as an answer. As if we take 2, then it is 3 into 2, 6. 6 into 2 is 12. So under modulo 9, it is 3. So again, we get the set B3. It means this B3 set is stabilized by all of UN. Similarly, the B2 set is stabilized by all of UN, and B4 set is stabilized by all of UN, and the empty set is obviously stabilized by all of UN. So these 4 gyro transfers correspond to the sets B1, B2, B3, and B4. Now for the isomorphism class of gyro transversals containing 3 elements, we have here order of UN is 3, and only proper divisor of 3 is 1. So here D is 1, and if we we have to take those elements from these sets such that the stabilizer GCD of stabilizer of those elements, order of stabilizer of those elements is always 1. Not that if we take any element from X, let us take a set B5 and multiply this set with 1, then we get the set B5. If we multiply by 2, we do not get the set B5. If we multiply by 4, we do not get the set B5. So B5 is stabilized by only one element, X1 here. So in this way, we choose exactly one element from X1. And if we take one element from X3, then it will stabilize. So it will not go with stabilizer of order 1. So for next step, we can choose 2 elements either from same set or one from each set. So if we take any 2 elements, say 1 and 2, and apply on B5, then we see that both this is stabilized by only one element. So order of stabilizer is again 1. So we can take one element from this set, 2 elements from this set, or we can take one from this, and in this way, we get the total number of gyro isomorphism classes 4, which correspond to the sets, these 4 sets containing 3 elements each. So in this way, we have found the total number of isomorphism classes of gyro transversals corresponding to set H in Dn, which is 4 plus 4, that is 8. Now, if we take the subgroup K, which is generated by 3x raised to power 3y, then we see that x equals to 1, x raised to power 1 plus 3k, x raised to power minus 1 minus 3k is a gyro transversals to H in Dn, where this small k is 0, 1, or 2. Then we see that the centralizer of this S in K is 1, x3, and x6. So the order of K here is 6, and order of centralizer is 3. So the order of this quotient is 2, and order of this D9 by this centralizer is 6, which is isomorphic to D3. And we know in D3, this gyro transfer is unique up to isomorphism. So by the result by Fogel and Ungar, we see that there is only one isomorphism class of gyro transversal, S to K in Dn. This is all what I have to say. Thank you.
Questions, please. Yeah, Ratan Lal, can you explain some origin of this gyro transversals? How were they originally?
Yes, ma'am. Actually, Fogel and Ungar in 2000, in this paper that I have cited here, yeah, in this paper, they actually introduced this concept, left gyro group and gyro transversal. Like, if we have a normal subgroup, then we have no distinction between left and right transversal. So, corresponding to a right gyro group, they think of transversal. What should be a transversal like? Because gyro groups are group-like structure. So they want to study if there is a transversal corresponding to a group, then what should be the corresponding notion in gyro groups? So they found that gyro transversal. So they introduced the concept of gyro transversal from there.
How do gyro groups arise in nature? Like,
yes, ma'am. Actually, this is determined by Ungar only in 1988. In the Einstein relativistic motion, the relativistic velocity addition do not form a group-like structure on the set of velocities, on the set of say vector field in R3. So after some time, Ungar realized that the Thomas gyrations, they can, with the help of these gyrations, they can recover that structure and make a new structure which looks like a group. And he noticed that this structure, he introduced this structure as gyro group.
and that was done in which year?
1988.
Okay, so are there questions, please, from the audience? Okay, so if there are no more questions, let's thank the speaker once again. Okay, so thanks. So our next speaker is Abhay Soman from University of Hyderabad. Is he there?
Yes.
Yeah.
Yeah.
So he will talk on triviality of reduced Whitehead group over Henselian fields. Over to Abhay, please.
Shall I start?
Yeah.
Okay. So thank you for the organizer for giving me opportunity to present my work here. Now I'm going to talk about the triviality of the reduced Whitehead group over Henselian fields. Let us begin with some notations and terminology. So for us, field is denoted by F, and A is a central simple algebra over field F. So that means the center of algebra is F, and it is simple as a ring, and the vector space dimension of this algebra over field F is finite. So Artin Wedenberg will tell us that it is a matrix algebra over a division ring, and the division ring D corresponding to algebra A, we often denote it by D, and we call it the underlying division algebra. And that division algebra is also central, and it is defined over F. Now with this notations, we define degree to be the square root of the dimension. So it is not difficult to see that the dimension of a central simple algebra will be square of an integer, and its square root, positive square root, we denote it as a degree. And next we define the index to be the degree of underlying division algebra. So for to give one example, so matrices over a field will be an example of central simple algebra, or classical Hamiltonian algebra over real numbers is also an example of central simple algebra. In fact, it is a division algebra. Okay. So we denote by A star the group of multiplicative units of A, and there is a reduced norm map from A to field F. Remember that field is the center of algebra A, and I'm not going into detail with respect to the definition of reduced norm. However, in order to give the analogy, you can keep the determinant of a matrix in mind. So here are two properties which are very similar to the determinant of a matrix. So reduced norm is multiplicative, and an element of the multiplicative group, if element of a central simple algebra is invertible, if and only if its reduced norm is non-trivial, non-zero. Okay, so one particular example, let us consider again the Hamiltonian algebra over real numbers and define a mapping gamma which maps I to minus I, j to minus j, and ij goes to minus ij under this mapping. Now, if you consider any element in this algebra, then the reduced norm of that element will be that element times image of that element under gamma. Okay, so it is not very difficult to see this. Okay, now to the definition of our main object of interest, namely the reduced Whitehead group. Now let us consider all those elements of algebra A such that the reduced norm of that element is 1. Collect all those elements of reduced norm 1 and consider the commutator subgroup of the group of multiplicative units of A. So it is denoted by bracket A star A star. So as we all know, it is generated by xy, x inverse, y inverse, where x and y are elements of A star. Now, as the definition goes, the reduced Whitehead group is defined as SL1A mod out with the commutator. Okay, so that is the definition. Here are some properties that are important to us. So for instance, if you have a matrix algebra over a division ring D, then the reduced Whitehead group of that algebra will be isomorphic to the reduced Whitehead group of the division algebra D. Okay. So what this property will tell you us that in order to compute the reduced Whitehead group of central simple algebra, it is enough to compute the reduced Whitehead group of underlying division algebra. As it is by very definition, the reduced Whitehead group is abelian group. In fact, it is a torsion abelian group. So let us consider now onwards, whenever we are going to consider reduced Whitehead group, we can assume that we are considering only division algebras. So if you put E to be the index of division algebra divided by the product of distinct prime divisors, then that E is the torsion, that the reduced Whitehead group will become E torsion. So this will give us that if the index of division algebra is square free, then the reduced Whitehead group is in fact trivial. Okay, and here is another property that says that if you have two division algebras D1 and D2 such that their index is co-prime to each other, then the reduced Whitehead group of their tensor product is actually isomorphic to SK1 of D1 cross SK1 of D2 as group. So this property will tell us that in order to study the reduced Whitehead group, we can study the reduced Whitehead group of central division algebra whose index is a power of a prime. Okay, so this property will reduce to the case of this particular kind of algebra. Let me give the connection with geometry. So Voskres and Scree has shown that the reduced Whitehead group of the division algebra is isomorphic to the group of R equivalence classes of SL1D. So R equivalence classes was defined for arbitrary algebraic variety by Manin, and that is a birational invariant of the variety. Because of this relation, very important condition that we have is that if the SK1 of D is non-trivial, then that will give us that SL1D is not a rational variety. So knowing only that our group, the reduced Whitehead group, is non-trivial, will give us an example of non-rational variety, and that is very important in the applications. So to give one example where the reduced Whitehead group is actually trivial, we consider the generalized quaternion algebra. So for that, we take two non-zero elements of field, and we construct an algebra which is generated by I, Z, such that I square is A, J square is B, and I and J are anti-committing with each other. So Hamiltonian algebra is a very particular case of this particular quaternion algebra. And in this particular case, we are assuming that the underlying field F has characteristic different from 2. Now, in this case, the reduced Whitehead group of this generalized quaternion will be trivial. Well, in fact, if you take any reduction of one element, then it is in fact a commutator. Okay, so more is known in this case, and this is a direct application of Hilbert's theorem 90. Before going further, let me quickly recall the cohomological dimension of a field. So consider a field E and Q be a prime number, then the Q cohomological dimension of E is the least integer D, such that the ith Galois cohomology groups will vanish for every discrete module A, which is a Q primary torsion, where I is any number bigger or equal D plus 1. So that is a Q cohomological dimension, and the cohomological dimension is simply taking the supremum over all Q, all primes. So it could be infinity, by the way. So just to give one example of L-adic field, so Q cohomological dimension will be 2 in this case. Okay. So let us come back to the reduced Whitehead group. So here are some known result. So for long, people actually thought that the reduced Whitehead group is always going to be trivial. So there were no known example earlier. So in 1970s, Platanow gave example of central division algebra over certain fields such that the reduced Whitehead group is non-trivial. So as we have remarked earlier, so this also provide an example of a non-rational variety SL1D. Okay. And point to be noted here for our case is that the example that he constructed has the field with cohomological dimension bigger than 3. Then there is a result of Jankowski. He says that if cohomological dimension of the field F is at most 2, then reduced Whitehead group is going to be trivial always. Okay. And then this is a result by Grenier-Bolle that says that if you have a field of characteristic P and take a prime which is distinct from that prime P and consider a division algebra of index a power of prime Q. Okay, Q is a prime different from P, and consider that Q cohomological dimension of underlying field is at most 2. Then he shows that SK1 is trivial in this case as well. So as you can see, if you have a cohomological dimension of field bigger than 3, then there are examples where the reduced Whitehead group is non-trivial. However, when you consider a cohomological dimension at most 2, it is always trivial. So the case of cohomological dimension 3, it is still very interesting. And here is a conjecture due to Suslin. So the conjecture is that if you consider field with cohomological dimension 3, then the reduced Whitehead group is always trivial. So this is still a conjecture. Only when algebras are of degree at most 4, then this conjecture is actually true. This is shown by Mercury by generalizing one of the result of Prost. Okay. So before going further, I will require a notion of valuation on division algebras. So this is valuation on division algebra is very similarly defined as in the field case. As you can see, the conditions here, 3 conditions that are exactly same as in the field case. So as with the field case, we attach some structure to the valuation. So namely the value group we denote by gamma D, then valuation ring. So all those elements whose valuation is bigger equal 0, the maximal ideal, then U, the group of units in the valuation ring. So that will be all elements of D whose valuation is 0. And then this is D bar, which is the residue division algebra. So here I would like to remark that so valuation on division algebra are very stringent in a sense that if value and in our particular this setup, we always assume that the valuation of division algebra is going to be the extension of valuation from the field F, that is the center of division algebra. And in this case, valuation, if at all it exists on division algebra, then this will happen if and only if the valuation from the field will extend uniquely to every subfield of D. So that is a very stringent condition on valuation. However, when there is a valuation on division algebra, it will give us very nice pleasant properties. So here is the notion of canonical homomorphism. This gives a path between the value group of valuation of division algebra and the field extension center of D bar over F bar. Here F bar is the residue field of the residue field of F under valuation V. So you can define like this. So there are some details one needs to check, but ultimately this is the definition. You begin with value gamma and consider a element of division algebra with value gamma. So call it D. And then you define theta D of gamma simply by X bar will go to dx D inverse of that, okay, modulo the ideal MD. Well, this is well defined and everything is good. So I will not go into detail for this homomorphism. So let's move on to the residue information. So again, we consider the same setup. And in this case, what is going to happen is that if at all valuation extend to a central division algebra, then that valuation is actually unique. Okay, so this is the first point here, that valuation is unique, and this is the formula of the valuation. And that center of the residue division algebra over the residue field of F is always a normal extension. Another very interesting property is that if you consider center of division algebra, the residue division algebra, over the fixed field of this theta D of gamma D, so image of gamma D under the canonical homomorphism. So this field extension is always a Abelian extension, okay? And the Galois group, so that is actually image of theta D of gamma D. And when we are going to see our particular case, so the canonical homomorphism will give very nice isomorphism between the residue between the residue class field and this value group. Okay, we will see that. So this can be found in, for example, Tinol Wordsworth book. Okay, so now to begin with our results, let us make some further assumptions. So we'll assume now onwards that our field has a valuation and that valuation is Hensel, and we denote the value group to be gamma F. Okay, and central division algebra D will have a valuation in this case because our base field is Henselian. So valuation extend and it extends uniquely to every subfield of D in this case. And there is another hypothesis that the characteristic of residue field is not dividing the index of D. Okay, and because of this condition, actually, and one of the result, actually the last point mentioned here, that will give us the isomorphism of groups. So gamma D, that was the value group of D under valuation, VD, modulo the kernel of theta D. Theta D is the canonical homomorphism. So this is isomorphic to the Galois group center of D bar over F bar. And we consider this n tilde to be the composition of filled norm with the reduced norm of residue division algebra. And we consider this zeta. So zeta is, in the literature, it's called the defect. Okay. All right. So here are some more groups. Those were studied by Irsha. So this, for instance, first group is related to the residue information, because n tilde is that map is from the residue division algebra to the residue field. Okay, and then there is second group CVD, and you can see that there is zeta eth root of unity in the residue field are coming into picture. So those play important role. And similarly, these groups are defined, and why we want to define that is the following result of Irsha. So he proved that this diagram has exact rows and exact column. Okay, so second row is exact is actually easy. Simply it follows from the definition of reduced Whitehead group essentially. Now here that h hat of -1 that is appearing is the -1th Tet cohomology group, and G, as we have described here, is the Galois group of that center of D bar over F bar. Okay, and the map from this SKVD to VD to -1th cohomology is actually defined by reduced norm. Okay, so one can show that these maps are well defined and the exactness is shown by Irsha. So our interest is computing the reduced Whitehead group. So if we are able to compute certain groups that are displayed in this diagram, or suppose we can prove that there is some collapsing between the rows, first row or the first column on that column, then we are able to get some information on reduced Whitehead group. So that's the motivation. Okay, so towards that goal, let us we have computed the cohomological dimension for this particular kind of fields. So before that, let us define the Q rank of the value group gamma F. So this is by definition is the dimension, vector space dimension of gamma F modulo Q over FQ, where FQ is a field with Q elements. Now we have shown that if field is Henselian valued and its residue characteristic does not divide prime Q, and let's assume that the Q rank is finite, then the Q cohomological dimension of field F and Q cohomological dimension of the residue field, they differ by the Q rank. Okay, so this is we obtained this result as a direct generalization of the discrete value, complete discrete valued case that is given in Sayre's Galois cohomology book. So this result will be important to us. So that will give us information about the cohomological dimension of residue field in terms of the cohomological dimension of field. Okay. So here is our main result. So we assume same hypothesis. Field is Henselian valued field. Characteristic of residue field is distinct from prime characteristic of residue field is distinct from the prime Q, and our division algebra has index which is a power of a prime Q. Now let us assume that the Q cohomological dimension of field is 3 and the Q rank is between 1 to 3. Then we are able to show that the reduced Whitehead group is actually trivial. So how this proof goes? So we have mentioned the result of Irsha and Kevasky, Grenier, Olay, and these results will be of course used, and that particular diagram of Irsha is what is going to be used here. And then there are result by Jacob Wordsworth and Tinol Wordsworth. They develop a theory of valuation on division algebra. Okay, so that results we are going to use, and here is very short idea of proof, and we will go case by case. Okay, so for instance, if Q rank is 1, then point to be noted are that the value group gamma D modulo gamma F, if you consider this group is actually cyclic, and because of the cohomological computation, we know that the residue field has Q cohomological dimension at most 2. So this will help us to prove that reduced Whitehead group is trivial in this case. Similarly, when the Q rank is 2, we have that the exponent of gamma D modulo gamma F is actually same as the exponent of this group. So commutator of D star modulo U comma D star, and remember U was the all those elements such that its valuation is 0. And another property in this case is that the n theta is actually surjective mapping, and the group defined by CVD is actually in fact the zeta ith roots of unity in the residue field. And after that, we will require to analyze the totally ramified part of T. So I'm not going to define it, but this is one of the result or condition that was developed by Jacob Wordsworth and Tino Wordsworth. So one can analyze that to get to the point that the reduced Whitehead group is trivial in this case also. So for Q equal RQ equal to 3 again, in this case, because of the residue information and the cohomological dimension, what we can assume is that in this case the division algebra itself is a totally ramified. Okay, and as it turns out, just as a side remark, in this case exponent and index is actually same, and this will again help to conclude that the reduced Whitehead group is actually trivial. Okay, so this is a very short idea of the proof, and I will stop with this. Thank you.
Questions?
Abhay, what is an example of the field F in your theorem? Some examples?
Some example. Okay, so one can start with any field of, let's say, you can start with C also, and you attach, consider the iterated LoRa series, then it will be like this field. So it will be Henselian with that ordering. So suppose C x1, x2, okay, iterated LoRa series. Then with x1, x2 adding valuation, it will become Henselian field. And the cohomological dimension, okay, you can take x1, x2, x3 as well. So cohomological dimension will be at least 3.
Mm-hmm. Thanks.
Thank you. Any other question, please?
Yes, Abhay, can you say a little bit about this totally ramified part you said?
Okay,
what is that?
Yeah, so we have this valuation. Let me go back. We have this valuation VD over division algebra, and actually there is assumption here that the characteristic of residue field does not divide the index. So these are something called tame division algebras. So that means that the vector space dimension of D over F is actually same as the vector space dimension of residue field over D bar over residue field into the index of gamma D over gamma F. Okay, and when it is totally ramified, we are saying that D bar and F bar are same. So residue division algebra is in fact the residue field. So okay, so point here is actually that theory developed by Canonical Wordsworth is that okay, so this homomorphism is there, right? So there is a kernel there, kernel of this homomorphism, but that kernel may not be equal to the gamma F, the value group of F. Okay, and that kernel theta D modulo gamma F will carry non-degenerate form, alternating form, and somehow that gives actually the totally ramified part of the division algebra.
Okay, thank you.
Abhay, do you also have results on the unitary reduced Whitehead group?
No, I don't have.
Okay.
Do you have some special results for the Schur subgroup of the Brouwer group?
Which subgroup?
On the Whitehead group? When your algebra is in the Schur subgroup of the Brouwer group, then can you have something? Do you have some special results for those algebras?
No, I don't. Did not get what kind of algebra you are talking about.
When your simple component, when your simple algebra is a simple component of a group algebra.
Oh, I see. No, I don't know.
Okay. So, are there more questions? Okay, so if there are no more questions, let's thank the speaker once again for a nice talk. So we come to the last lecture of this conference. This is by Carmine Monete from Italy, University of Salerno. Yeah, is he there?
Yes, I'm here.
So he will speak on the construction related to non-abelian tensor square of algebras. So over to Carmine, please.
Can you see the presentation displayed? Okay. So, good afternoon or good evening, maybe to you there in India. Thank you to the organizers for the opportunity to give this talk in this very well-organized conference. As you see, as the organizer said, I will talk about on a construction related to the non-abelian tensor square of a group. And this is a joint work with people from Brazil, Noraí Rocco and Raimundo Bastos from University of Brasilia, and Ricardo Gio Oliveira from Universidad Federais of Goiás. And you can find this preprint paper on arXiv. We just submitted. So, okay, so let me start introducing the main character of this talk, which will be the non-abelian tensor square of a group. So, given a group G, we will define a group with a presentation. So, which generators are these symbols, GO times H, with GL and H running in capital H, satisfying these relations. So for every GHX in G, we have these two equalities holding. Let me say that here we are using the left notation. So G to the H means the conjugate of G by H, which is H minus 1 GH. The elements G O times H will be called tensors. And if G is a finite group, you can see that the non-abelian tensor square is given with a presentation with the square of order of G generators and twice the order of G cube relations. Okay, but just a slight change in definition, you can get from the relation of the non-abelian tensor square to the expansion formula of commutators. So just replacing the O time symbols with the brackets, you get the same formulas for commutators, which holds in every group. Let me also say that here the commutator is in the left norm. So GH bracket means G minus 1 HX minus 1 GX. Okay, and I think I love to mention this statement from Luis Cappe, who says that it was this visual similarity that led me to look into this topic. And I think that many mathematicians started studying the non-abelian tensor square due to these similarities. Okay, but actually these similarities let us to define a map from the non-abelian tensor square to the derived subgroup G dash of a given group G, which is just take a tensor, G tensor H, and send it to the commutator between G and H. And this is well defined due to the relation, the defining relation of the non-abelian tensor square. Actually, this map gives rise to a topological significance for the non-abelian tensor square, Indeed, in their paper, Brown and Lodey presented a topological meaning for the non-abelian tensor square of a group. Indeed, if you take a topological space with just one homotopy group, the first one, isomorphic to G, and all the other trivial, then the third homotopy group of a suspension of this topological space is actually isomorphic to the kernel of the derived map. So it is interesting to study the non-abelian tensor square and also its normal subgroups, μ of G, in this case, to get information on this topological group. Topological group, yes, and also to the topological space. Okay, but in this talk, I will go more to the group theory point of view. And the starting point from the non-abelian tensor square of a group, from a group theoretical point of view, started with Brown, Johnson, and Robertson, who followed the unpublished paper of Dennis in search of new homology functors having a close relationship to K-theory, and the paper of Miller. Actually, in this paper, Brown, Johnson, and Robertson computed the non-abelian tensor square for all non-abelian groups of order up to 30. And they did it up to this order because they used the Tits transformation. You can see to use this kind of method, you need to have little group. And so since you have the square of G generators and twice the order of G cube relations. So it is interesting, given a group, to understand who is the non-abelian tensor square. One method is this one, to use Tits transformation, so just the representation. Another one could be to use universal properties. I mean, we can, given two groups, G and L, we define a biderivation, or also known as cross-pairing, from G times G to L, a function which satisfies these two properties. So whenever you take A1B, it goes to the image of the conjugate of A1B to the A1, and the image of A1B. And something similar on the other side. Clearly, if we get the map from G times G to the non-abelian tensor square of the group G, which sends each couple to the tensor between G and H, this is a biderivation, and this is due to the fact of the defining relation of the group G tensor G. Okay, this kind of biderivation determines a unique homomorphism from the non-abelian tensor square of G, G O times G, to L, which makes this diagram commutative. Okay, so whenever you find a biderivation F from G times G to L, you get an homomorphism from G O times G to this group L. So if you want to use this kind of method, you have to guess both the group L and the biderivation. So it is actually an improbable task. No one can say, okay, this is the group, and then you get the biderivation. But if you are in some special cases, it seems easy. Okay, but other kind of method you can use to get the non-abelian tensor square, which is the one we preferred, I said our team studying the non-abelian tensor square, is a related construction. I mean, if you get the group L if you get a group G, you can construct another group, which is the group Ni of G. I will present it you, introduced by Rocco in 1991, which has the non-abelian tensor square as a subgroup. Okay, so you start from a group G, you take G phi, an isomorphic copy of G. So we will denote with the G to phi the elements of this copy. And then we consider the following group. So Ni of G is the group generated by G and G phi, with their relation, of course. And then you get you put these conditions. So whenever you consider a commutator between an element of G and an element of G phi, you can conjugate it with an element of G, for instance, G3, and this is the same as conjugated it with its image via phi, so G3 phi, and you can enter in. So you can forget about the brackets and enter and conjugate the elements G1 and G2 in G. Okay. This kind of construction makes easy to see that if you consider the subgroup generated by this commutator between an element of G and an element of G phi is a normal subgroup, because whenever you consider a generator, you can enter inside with you get the conjugate of a generator is again a generator of this group. And so the group Ni of G is actually an iterated semidirect product of upsilon1 of G times G phi, since these two subgroups G and G phi commute modulo upsilon1 of G. Okay, but why is interesting to study this group? The motivation is the commutator connection. In his paper, Rocco showed that the map which sends each tensor, G tensor H, from the non-abelian tensor square of the group G into the commutator between G and H phi, this is actually an isomorphism. So what we get is the following. We have that the non-abelian tensor square is embedded in the derived subgroup of the group Ni of G. So whenever you want to investigate the subgroup, the non-abelian tensor square GO times G, you can just use commutator calculus. So you can forget about these O time symbols and use just group theory. Okay, but for instance, a first application of this group, this construction, appear with this presentation for the group Ni of G. If you remember, I said that using Tits transformation is hard when the group has order more than 30. Here, McDermott and Rocco independently get a simplified presentation for Ni of G, wherever G is a polycyclic group. So for instance, if you say G is a finite group and G is soluble, then you can get always the non-abelian tensor square of this group, just getting the presentation of the group Ni of G, and then its subgroup upsilon1 of G. What we want to say today, what I want to say today is that actually this group gives many information about the group upsilon1, about the non-abelian tensor square. Okay, so just let me start with the description of the subgroup lattice of this group Ni of G. You can get, for instance, the epimorphism from Ni of G to G, which sends each element of G in itself and G to phi in G. This is actually the map which forgets about the phi symbols. Okay, so if we denote by theta of G, the kernel of this map rho, then we get that Ni of G over rho of theta is isomorphic to G. And this is a normal subgroup which will play an important role in this talk. Okay, we have an homomorphism. We can restrict this homomorphism to the non-abelian tensor square, so to this upsilon1 of G. And if we restrict also the image in the codomain, we get an epimorphism from the non-abelian tensor square upsilon1 of G to G dash, just sending the commutator G H phi, forgets about the phi, to the commutator between G and H. Actually, this map rho dash is nothing but the derived map I defined at the beginning. Okay, so the kernel of this new map is actually the subgroup I defined at the beginning, Ni of G, which is the intersection between the subgroup theta of G and the subgroup upsilon1 of G. And okay, first homomorphism theorem says that upsilon1 of G over Mi of G is isomorphic to G dash. But what is interesting is that this subgroup actually is a central subgroup of Ni of G. So zeta of Ni of G denotes the center of this group. Just the last subgroup I want to mention is the diagonal subgroup. So the subgroup generated by all the commutator between an element of G and its image via phi. So G phi, with G running in capital G. These generators belongs both to the subgroup upsilon1 of G, because you are taking a commutator between an element of G and an element of G phi. But if you forget about the phi symbol, you get a commutator between G and G, which is trivial. So actually this subgroup is contained both in theta, both in upsilon1 of G, which is the which intersection is actually the subgroup mi of G. So also the diagonal subgroup is a central subgroup of mi of G. And what is interesting is the fact that mi of G has an interesting quotient. If we quotient mi of G over this delta, we get the Schur multiplier of the group G, which is actually the second homology group with integer coefficient of the group G, which we denote with H2GZ. Okay, so up to now, we have this description of the subgroup lattice of the group Ni of G. So we have interesting subgroups like upsilon1 of G, which is isomorphic to the non-abelian tensor square. We have interesting quotients, so section of the group Ni of G, like this magenta one, Mi of G over delta of G. But there is also another interesting section, which is the quotient of upsilon1 of G over the delta subgroup, which is actually isomorphic to the non-abelian exterior square of G. So studying the group Ni of G gives a lot of information. So all the properties that are preserved respect to section, taking section, or taking subgroups, and you can discover these properties on the group Ni of G, you get for free on this subgroup lattice. Okay. There are a lot of properties that are preserved by this Ni symbol. So if we start with a finite group G, then Ni of G is finite. If you start with a P group G, then Ni of G is a P group again. So one of the problems really studied by now about the non-abelian tensor square is to relate its exponent to the exponent of the group G. And for instance, if you get a bound for the exponent of Ni of G, you have for free a bound for the non-abelian tensor square. But actually this bound is not so sharp because we have seen at the beginning that the Ni of G over upsilon1 is isomorphic to G times G. So the exponent has this order of G square, which is a bit far from being sharp. Okay, but I said that upsilon of G is actually a subgroup of the derived subgroup of Ni of G. So if we consider the derived subgroup of the group Ni of G, which has this description, so it's an iterated semi-direct product of upsilon1 of G times G dash times G dash the G phi dash. If we get a bound for the subgroup, the derived subgroup, a bound for the exponent of the derived subgroup, again, it seems that the exponent of the non-abelian tensor square is not sharp because we have this G dash and G phi dash, the exponent of the derived subgroup of G that plays a role. But actually, what I want to show you today is that the last statement is false. Actually, if you get an exact bound for the exponent of the derived subgroup Ni of G dash, then also the exponent of upsilon1 of G is the same. And this is due to this result. So we had this description as an iterated semi-direct product of the group Ni of G with a normal subgroup. Upsilon of G is normal, but the subgroups G dash and G phi are not normal. So this is just a semi-direct product. What we showed is that the derived subgroup of the group Ni of G is actually the central product of 3 copies of the non-abelian tensor square. So upsilon1 of G, upsilon2, and upsilon3 are 3 subgroup, normal subgroup of Ni of G, each one isomorphic to the non-abelian tensor square Go times G, and they gave rise to a central product. So they are pairwise commuting. The intersection between 2 of them is a central subgroup. Actually, the intersection between upsilon1, upsilon2, upsilon2, upsilon3, and upsilon1, upsilon3 is the kernel of the derived map. So that subgroup Mi of G I've defined previously. So now I will just to show you how to consider these subgroups upsilon2 of G and upsilon3 of G, because upsilon1 is clear that is a subgroup of Ni of G dash. Okay, The first subgroup we considered, upsilon2 of G, is the commutator subgroup, so the interderivative of the theta of G subgroup and G. And after some commutator calculus, we get this presentation. So we get that the subgroup upsilon2 of G is actually generated by this kind of elements. So you take a commutator between G and H, and then you multiply it by the commutator between H and G phi, with G and H running in G. Okay, after we found this kind of description, we thought about a function from G times G to this subgroup upsilon2 of G with this kind of properties. So sending the couple GH to the generators. What we show is that this is actually a biderivation. So we prove that the gamma satisfies the two properties of a biderivation. And so there exists a unique homomorphism from GO times G to upsilon2 of G, this gamma star. And what we prove is that this is not only an homomorphism, but this is an isomorphism between the group upsilon2 of G and the non-abelian tensor square. Okay, so this is a case in which you get for free a map. This map has good properties, seems to be a biderivation, and then you can get use universal properties to get a new copy of the non-abelian tensor square. Okay, how to get the other copy? If you look at the definition of upsilon2 of G, this is the commutator between theta of G and the subgroup G. So it can be, what I can say, forward to ask what if I substitute G with the G phi. And actually, we can extend the little phi isomorphism between G and G phi to an isomorphism from ni of G to itself, which sends an element without G without phi with an element with phi. So G goes to G phi and G phi to G. So the subgroups, for instance, upsilon1 of G, theta of G are phi, capital phi invariant subgroup, because if you took away this phi symbol and you put where it isn't, you get the same generators. While the subgroups G and G phi are not, because G is sent to G phi and again G phi to G. Okay, so the other group we get, upsilon3, this subgroup, is the image of upsilon2 via this phi isomorphism. So again, since this phi is an isomorphism of ni of G, we get that upsilon3 of G is again isomorphic to the non-abelian tensor square of G, of the group G. Okay, what next? For instance, this description for the derived subgroups helps to describe also the derived subgroup, the derived series and the lower central series of the group ni of G. So also for these groups, we had a semi-direct product description. Now we can give a new description with normal subgroups, pairwise commuting. So all the calculation about nilpotency or exponent problems can be solved easily. And okay, just I want to mention that now the picture is a bit more complicated. I mean, with more subgroups, more interesting subgroups. And what we proved is that this green line, I mean, the ni of G over upsilon1 and theta, and also the other one, are isomorphic to the abelianization of G. And we gave a proof of this for every group G, so not depending on the finiteness of the group. Also, all the black lines in this picture says that the quotient, since these are all normal subgroups, the quotients are all isomorphic to the derived subgroup of the group G. And I mean, we hope that this new description of the derived subgroup will help to solve problems in the spirit of this group, Ni of G. And that's all. Thank you very much.
Questions?
Yeah, I have a small question. You at the end you said you feel that these constructions will have some applications. So could you please indicate the kind of applications you might get, like on?
Yes. So if you have a group, Ni of G dash, for instance, and you you know that this group is the central product of three groups.
Yeah.
If you get that this group, for instance, is nilpotent of a given class, you get nilpotency class for the same subgroup. So since these subgroups are pairwise commuting, the nilpotency class of the group Ni of G dash is the same as the nilpotency class of the non-abelian tensor square. So you get information studying the group Ni of G, which is just a group with a presentation. You use commutator calculus, you forget about the symbols all times, and you get for free information of on this non-abelian tensor square. Again, if you consider, for instance, exponent problem, and you get a sharp exponent bound, a sharp bound for the exponent of Ni of G dash. For instance, there are many people studying the exponent of the non-abelian tensor square when G is a finite P group. And they are trying to relating this exponent to the exponent of the group G. Then, for instance, if you get a sharp bound for the exponent of the Ni of G dash, you get the same for the exponent of Go times G. Okay. For instance, you can study the number of generators of the non-abelian tensor square. Now that you have that the group Ni of G dash is actually the central product of three copies of the same group. If you get information about the group Ni of G dash, you also can get information about. This is actually a new direction we are thinking about. Starting from a given P group, for instance, and finding information about the number of generators of the non-abelian tensor square of this group. And maybe this question can help. Also, if you are looking for commutator relations, for instance, if the non-abelian tensor square satisfies a commutator identities, you can just get these commutator identities on the group Ni of G dash, and then for free you get on this subgroup. I don't know if I was clear about the
because you know, if you have information on the generators of G tensor G, then you suddenly can use this information on study of Sur multipliers and other stuff like that.
Yeah, it's actually this.
Okay, thank you.
Are there more questions?
So yeah, I have one question. So this result is known that if the commutator subgroup of G has class C, nilpotency class C, then the G tensor G has nilpotency class C or C plus 1. So that type of result can be verified by this result.
So you said that if the group G has nilpotency class C,
the commutator subgroup of G has if nilpotency class C, then G tensor G has nilpotency.
Yes, it is nilpotency class C or at most C plus 1.
So
yes, you can get this information from this description.
Okay.
Because you have information about the derived. Let me go forward. No, sorry. Here, for instance, if you look at the gamma k of Ni of G, this is just the product of these subgroups. Okay, you can use the new description, for instance. So you have information about the group G. So if say K, in this case we have K, not C, but if the nilpotency class is K, then you get these two subgroups are trivial, and just you have to study the gamma K G dash, G phi, sorry.
Okay.
So you get this information from this construction, you can get it.
Okay, and also if, so can you go to that slide, that result? Yes, so this is just central product of 3 copies of this G tensor G. So from here, can you tell if G tensor G has nilpotency class C, then what about the nilpotency class of nu G prime?
No, sorry, I didn't get the question. Sorry.
How the nilpotency class of the G tensor G and nu G prime here are related?
No, I said if you have the nilpotency class of ni of G dash.
Yes.
So it has a nilpotency class, say C. Since these subgroups upsilon1, upsilon2, and upsilon3 are pairwise commuting, so the C plus 1 term of the lower central series is just the product of the 3.
Yes.
And so you get the information about the nilpotency class.
Okay. Thank you.
Thank you for your question.
Any other question, please? If not, let's thank the speaker once again.